In this example, we're told we have a hydraulic cylinder with its motion cushioned at the end of its stroke by a piston that enters a hole as shown below. So the cylinder is moving downward into this piston region. So it's moving downward, and as it moves downward, what happens is there's hydraulic fluid in here that gets pushed upwards and out. So as this inner cylinder comes down, the movement is slowed down because you're also pushing out the hydraulic fluid. And we're asked to find the average velocity at which the hydraulic fluid escapes from the hole. So we're trying to find the velocity out in this region, assuming that the cylinder moves downward at a constant speed v cylinder. And then once we know that, we're also asked to find the velocity with relative uncertainty for the following conditions. So this is a measurement uncertainty, propagation of uncertainty kind of problem. All right, so if we're going to find the velocity out, this is a conservation of mass type of problem because we're trying to find the velocity out. We're conserving mass. As the cylinder comes into this region, then in order to conserve mass, we have to have some mass going out because the walls of the outer cylinder are rigid. Okay, so it's a conservation of mass kind of problem. It's first important to recognize the physics of the problem, what's really happening here. Now that we know it's conservation of mass, what we need to do is apply conservation of mass. So let's go ahead and write it out. Conservation of mass. It's good to start with your governing equation. So just a reminder what these various terms are. This first term, just the integral part, this is the mass inside the control volume. And so this is the time rate of change of mass inside the control volume. And then this is the net rate, the net rate at which mass leaves the control volume through the control surface. Remember that this expression is just a little bit of mass flow rate. So when you integrate it over the whole control surface, you get the total mass flow rate out of the control volume. So now we need to choose a control volume. You always need to show a control volume when you apply conservation of mass. So the one that I'll choose, I'll actually use two in this problem, but let me just show the first one that I think is easiest to work with, is one that just follows the interior of the cylinder, cuts across where the fluid's going out, and then also moves with the inner cylinder. Okay, this is actually a deformable control volume. I'm going to have this control volume actually move with that inner cylinder. So as this inner cylinder moves down, the control volume just kind of hugs it and also moves with it. So it's a deformable control volume. And I wanted specifically to cut across here because I'm trying to find the velocity out. So I want my control volume to cut across right there so that velocity out will show up in my analysis. All right, so now that I have my control volume, let's go ahead and start evaluating the various terms in my equation. So first of all, we'll evaluate the time rate of change of mass within the control volume. So again, this is just like saying ddt of the mass inside the control volume. It's the same kind of thing. So when I draw, let me write out what the mass in the control volume is. The mass in the control volume will be the density times the volume of the control volume, right? Well, the density is a constant, so I can pull that outside. I'm assuming that the hydraulic fluid is incompressible. So now I have the time rate of change of the volume of the control volume. And so when I look at that, the way I can write the volume is it'll be the volume of this big cylinder based on the outer radius, capital R, and then I'll subtract out the volume of this inner cylinder. So let me write that down. So this will be the density times the time rate of change of the volume of the outer cylinder, which is pi capital R squared times L, that's this distance here, minus the volume of the inner cylinder, which is pi times little r times x. X varies here, it depends on the time. All right, and now let me go ahead and take the derivative through. Well, the derivative of this term is 0 because these are fixed quantities. Pi, of course, is fixed. Capital R squared and L, those are just constants. They just describe the geometry of the outer cylinder, so they don't change. But what does change here is the x. The little r, again, doesn't change. It's part of the geometry. But x does change because the distance that it's moving down here will change with time. So when I take the derivative, I'm going to get the following. A minus pi, oops, I should keep the rho out front. Minus rho pi r squared times dx dt. So that's how the mass inside the control volume changes with time. Now I can simplify that a little bit further by recognizing dx dt. That's just how this distance is changing with time. If you look at that for a moment, that's just v cylinder. It's just how that distance changes with time. It's just v cylinder there, right? So this is really minus rho pi r squared times v cylinder. So that's that term. All right, now let's move on to the mass flow rate term. So there, let's go ahead and just rewrite it. So here, the only place where we have mass coming in or out of the control volume is just right up here at these points. Everywhere else, it's a solid boundary, so there's no mass coming in or out. And it doesn't even come in down here either, because remember, this part of this control surface moves with that inner cylinder. So the cylinder never enters the control volume because the control volume is moving with it. So the only place where stuff is coming in or out is right there. So let's evaluate the integral at that point. So we have the density times the velocity, the relative velocity there. Well, up here the control surface isn't moving, so it's just the fluid velocity. So let's put a coordinate system here. Let's call that the y direction. So here the relative velocity is just v out. It's the same v out all the way around. Oops. And that's in the j hat direction using my coordinate system. And then the area there is just going to be, it's going to be the area of an annulus. You've got, if you look at this from above, it looks like something that looks like this. This is the inner radius little r, and this is the big radius capital R. And so the area is actually this area. So it'll just be pi r squared, big R squared minus little r squared. And that's also in the j hat direction, because that normal vector for that area is pointing outward. So it's just pointing in the positive y direction. Remember, for the areas, we use an outward pointing unit normal vector. So here's my control volume. So pointing out here is in the upward direction. So again, just a refresher, here's my density term. This is my relative velocity term. Again, the control surface doesn't move at that part of the boundary. Fluid velocity is just v out in the y direction. This is the area there. It's just the annulus. And that outward pointing normal points in the j hat direction. So we can do the dot product. And we'll get rho v out times pi capital R squared minus little r squared. So that's this term. So we can now combine them together. We'll have the time rate of change of mass inside the control volume is just this term we evaluated earlier. And then here's our net mass flow rate out. Sum those together and it should be equal to 0. You can see a density and a pi drop out. And we're trying to solve for V out, so V out will equal V cylinder. And then it'll be capital R squared over little r squared minus 1. If I've done my math correctly there. Let me just double check. Actually, I have it flipped the other way. Sorry about that. It should be little r squared over capital R squared minus little r squared. Yes, that is now correct. So that's my velocity out. All right, so I said that there are actually two different ways to do this. So let me go back and draw a different control volume. Let me choose a control volume now. It still goes on the outside of the, that goes on the inside of the outer cylinder, but now let me just cut straight across. Let me use that control volume. Okay, so in that one, we'll evaluate our different terms. So here's the time rate of change of mass inside our control volume. So we just said that that's like a ddt of mass inside the control volume. So the mass inside the control volume will include the mass of the hydraulic fluid. So that'll be the hydraulic fluid's density, I'll just call it rho, times how much of that volume is hydraulic fluid. So that'll be pi capital R squared times L. That's the volume of the outer cylinder, minus pi little r squared times x. That's the volume of the inner cylinder. That's just this one. And then, so that's just the volume of the hydraulic fluid. And then inside this control volume, I also have the mass of the cylinder itself. So I have to include that in there. So I'll add in the density of the cylinder times its volume, which is pi little r squared times x. So that is now my new mass inside the control volume using my new control volume. And then we can go ahead and carry through the time derivative. So the time derivative of this is going to be 0 because those are all constants. And what we'll end up getting is rho, be minus rho pi r squared dx dt plus rho cylinder pi r squared dx dt. And we already know that the dx dt is just the velocity of the cylinder. We figured that out from before. So this will be minus rho pi r squared v cylinder plus rho cylinder pi r squared v cylinder. Okay, so that's what we have now for the time rate of change of mass inside our control volume. Now let's do the mass flux out of the control volume through the control surface. Okay, again, when we go back up to the control volume, the only place where mass is coming in and out is right here. And so mass is going out, the hydraulic fluid is going out in that same annulus that we did previously. But now we have mass coming in because we have the cylinder moving downwards, so there's actually some cylinder mass that's coming in. So let's write out these terms. So as we found previously, the mass flow rate of hydraulic fluid leaving looks like this. So that's what we found previously for the hydraulic fluid. Now we have to account for the mass that's coming in because of the cylinder coming in. So that'll be the density of the cylinder. The velocity at which the cylinder comes in, so the relative velocity, the control surface isn't moving, so its velocity is 0. And the velocity of the cylinder coming in is minus v cylinder in the j hat direction. So it's moving downward, so it's in the minus j hat direction. So that's going to be minus v cylinder j hat. And then the area through which it's coming in will just be pi little r squared times j hat. Because that's this area right here. And the normal vector, of course, is still pointing upward and outward. So that's this area is just the pi r squared in the positive j hat direction. So that's that term. So now we can simplify this. And then this term will be a negative rho cylinder v cylinder times pi r squared. All right, so that's now our net mass flow rate out of the control volume expression. So now we'll just add the two together. So we're going to add this together with the other double underlined item. So this comes from our time rate of change of mass in the control volume, and then we're adding in the net mass flow rate out. And what you've probably already see here is that this term will cancel out with that term. And what we're left with in the end is V out will still be V cylinder times little r squared over capital R squared minus little r squared, which is exactly the same result that we had previously. It's right there. So you see that we get the same result regardless of control volume, and that should always be the case. Your result for V out here, it shouldn't matter what control volume you choose. It should always be the same result. It's just some control volumes are a little easier to work with than others. Personally, I find our first method, where our control volume, let me just kind of sketch out these two control volumes. Again, I'll draw one in blue and one in red. So the first one we did was in blue here, where it was actually a deformable control volume that moved with the inner cylinder. I prefer that one. That one makes a lot more sense to me. But you can also use this red one that's not deformable, but the cylinder, you have to account for the cylinder mass coming in and how that mass changes what's inside the control volume. So, 6 of one, half dozen of another. It's whatever you're most comfortable with. But you get the same result. All right, so the next part of the problem is to find the uncertainty in the velocity going out given the uncertainty in these other values. So that's a propagation of uncertainty problem. So we're trying to find the relative uncertainty in V out, and given the relative uncertainties or uncertainties in the other values. So we're going to have the relative uncertainty in V out due to the uncertainty in V cylinder squared, plus the relative uncertainty in V out due to the uncertainty in little r squared, plus the relative uncertainty in V out times the uncertainty in capital R squared, and take the square root of the whole thing. Okay, and if you go up here for a moment, you'll see that in the problem statement, we're also given, the uncertainty in L and the uncertainty in rho. Turns out that doesn't matter, right? When you look at our expression for V out, those don't show up anywhere in here, so those quantities don't make any difference to us. So now at this point we have to find those relative uncertainty terms, and that is where we make use of our partial derivatives. So this will be 1 over V out times dV out dV cylinder times the absolute uncertainty in V cylinder. So we can substitute in so dV out to dV cylinder will just be little r squared over capital R squared minus little r squared. You'll see that the r squared terms cancel out, and what we're left with is just absolute uncertainty in V cylinder over V cylinder, which is just the relative uncertainty in V cylinder. So that's that term. Then we can do the other ones. They're a little more complicated. So here I'm doing the expression for the relative uncertainty in V out due to the uncertainty in little r. So we follow the same procedure. This one is a little more complicated because the derivative, we have the little r squared that's in both the numerator and denominator, so you'll have to actually use the like the division rule. And unfortunately, I didn't work that out in advance, so I'm not going to work it out here. It's just standard calculus. The way I would do it is I would rewrite. I would do it like this. I would do ddr of r squared times r squared minus r squared to the minus 1 like that, and then take the derivative of that using kind of the multiplication rule. Okay, and then you can do the same sort of thing to find the relative uncertainty in V out due to the uncertainty in capital R. Like I said, I'm not going to run through the calculus on these. I don't think anyone wants to sit and watch me kind of work all that out. I'm just kind of giving you the setup for how you would go about doing it. Okay, so if you know how to do this part, you're in pretty good shape. Once you have all these, you can plug them, of course, back into up here. And we can then evaluate what the relative uncertainty in V out is. And if you work through all those quantities and plug in the actual values that were given. If you go back up to the problem statement, you'll see we're given R, big R, little r, V cylinder. So if you plug in all those values and then work out the relative uncertainties, I'll just give you the final result. You'll get that V out comes out to be 80 plus or minus 3.6 millimeters per second. So that's the measurement uncertainty part of the problem. Hopefully the measurement uncertainty makes sense. The only thing that's tough about that is just doing these derivatives. They can be very tedious. So you can either do them by hand or you could use a calculus kind of package like Wolfram Alpha to do it for you. But hopefully you understand how to do this measurement uncertainty part. The main thing I really wanted to go through in this example was the conservation of mass portion, and I wanted you to see the two different control volumes that you can use. So make sure you understand how to do the conservation of mass part of this problem. All right, we'll go ahead and end it there.